Today, I want to ask you, why Analog CDR? Let's start with the advantage of Analog CDR, because it is important to understand why this architecture has worked so well for many decades. Analog CDR is simple, fast, and proven in silicon. It is not an outdated or bad architecture. For many applications, it is still a very reasonable design choice. So let's first understand what a CDR does quickly and why the analog implementation became the traditional solution. A clock and data recovery circuit over a CDR recovers the sampling clock from the incoming data. You can think of it as a PL with a divide ratio of 1. However, there's one important difference. In a normal PL, the reference clock usually has an edge every cycle. In a CDR, the reference information comes from the data transition. If the data contains a long sequence of zeros or ones, there may be no transition for several unit intervals. During that time, the CDR receives no new phase information. The loop must continue running and maintain the correct sampling phase until another data transition appears. A typical receiver contains data slicers, edge slicers, a deslicer, equalization circuits, and a clock recovery loop. The job of this loop is simple to describe but difficult to implement. It must create a clean sampling clock and place the clock near the center of the data eye. You may ask why we do not simply send a clock together with the data. The problem is that the clock and data can experience different delay, skew, and jitter through the package, board, and channel. Therefore, at high speed, it is often better to recover the timing directly from the received data. This is the traditional Analog CDR architecture. We have a phase detector, a charge pump, a RC loop filter, and a VCO. The receiver clock is fed back to the phase detector, closing the loop. The phase detector decides whether the sampling clock is early or late compared with the data transition. The charge pump converts that early or late decision into current. The current charges or discharges the loop filter capacitor. The capacitor voltage controls the VCO frequency. If the recovery clock is too slow, the loop changes the voltage control and speed up the VCO. If the recovery clock is too fast, the loop changes the voltage in the opposite direction. One important advantage is the charge pump PO that can provide type 2 loop behavior. This allows the loop to track a constant frequency offset with approximately zero steady-state phase error. The entire correction path is continuous time. Phase error becomes current. Current becomes voltage. Voltage controls frequency. There's no digital processing pipeline and no digital calculation delay inside the basic loop. This direct signal path is one of the biggest strengths of the Analog CDR. Many Analog CDRs use an Alexandra or Ben phase detector. Why is the phase detector so popular? The first reason is simplicity. The phase detector mainly asks one question: is the recovery clock early or late? If there is no data transition, the detector may produce no useful phase update. Therefore, we can think of the output as having three possible conditions: early, late, or no transition. In digital terms, these are similar to +1, -1, and 0. The second advantage is robustness. The phase detector does not need to accurately measure the size of the phase error. It only needs to determine the direction of the error. That makes it relatively tolerant to circuit mismatch and process variation. But the Ben detector is nonlinear, so the loop may have a limit cycle behavior or hunting near lock. However, this behavior can be analyzed and modeled. So, even though the detector is nonlinear, we still have a useful engineering model for designing the loop. The band-band facilitator is simple, robust, fast, and well understood. Now, let us look at the real strengths of Analog CDR. The first strength is the low loop latency. The facilitator creates an error. The charge pump immediately changes the loop filter voltage. Then the VCO responds. There's no decimation, no digital pipeline, and no multi-cycle calculation. Low latency is very valuable because loop delay limits how much the loop gain and bandwidth we can safely use. The second strength is implementation simplicity. The loop filter may require only a resistor and a capacitor. The oscillator is a natural analog oscillator, such as a ring VCO or LC VCO. We do not need a large amount of digital logic to perform the loop calculation. The third strength is the demonstrated high-speed operation. Analog CDR reaches multi-gigahertz per second data rates, even in older CMOS technology. For example, published design demonstrates tens of gigabits per second operation using half-rate facilitator and interpolating VCO. The half-rate architecture allows the internal clock to run at half the data rate. This can significantly relax the speed requirement of the internal circuits. Therefore, Analog CDR offers three very strong benefits: low latency, a relative direct implementation, and proven high-speed performance. These benefits explain why Analog CDR was the standard architecture for so many years or even decades. Analog CDR can still be the correct choice when the operating conditions are relatively simple. For example, the data rate may be moderate. There may be only one lane or a small number of lanes. The channel and operating environment may be stable. The design may not need extensive digital calibration or internal state readback. You may also not need to change the loop bandwidth after the chip is manufactured. In this case, a traditional analog loop may provide a lower overhead solution. This can be especially true in an older process technology, where the digital logic may consume more area and power than it would in an advanced node. Analog CDR may also be attractive when a very low latency is the honest priority. However, notice the assumption I'm making here: a moderate data rate, a stable channel, a small link count, and limited need for observability and programmability. Analog CDR works very well when these assumptions are valid. The difficulty begins when the real system validates several of these assumptions at the same time. Here are the summary images showing you why Analog CDR is still a good choice for you. The Analog band-band CDR is a proven and elegant architecture. It has a very direct signal path. It offers low loop latency. It can be built with a charge pump, an RC loop filter, and a VCO. It also has decades of successful silicon results behind it. Its behavior is supported by a special PO and band-band CDR theory. Therefore, Analog CDR is not simply an old architecture that should always be replaced. For stable link with a moderate data rate and limited programmability requirements, it may still be the best solution. However, modern systems often have many lanes, wide PVT variation, dynamic channels, background calibration, and complex debug requirements. Under those conditions, the weakness of the analog loop becomes much more important. In the next video, we'll look at those weaknesses. We'll discuss control voltage range, capacitor linkage, loop filter area, PPT sensitivity, and the difficulty of observing and freezing an analog loop. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please your comments down below. Lastly, please share the video with the people who may be benefiting.